any two functions is the maximum or the supremum of the, it's basically the biggest distance it achieves or approaches. Okay. So here's a question for you. What's the neighborhood around a particular function going to look like? This is kind of fun, actually. Give me an epsilon ball around F. What is an epsilon ball around F going to look like? Willie? If you did what? Yeah, if you did the function in bold, if you put a little ribbon around this function, it's any other function that lives in a ribbon. Sorry, I'm going to stop dotting, but I'll just put a little ribbon. And Willie said, think about it in bold. If I put a little ribbon around this, to be in an epsilon neighborhood around F is any other continuous function that lives in this ribbon. Are you with me? That's what it means. That's what an epsilon neighborhood is. Yes? Oh, excellent. So you could imagine, you could talk about covers of sets, right? An open set of functions is basically a function, a set of functions, such that for any function in that set, you can perturb it a little bit and it's still in that set. Perturb it within a ribbon. Yes? Oh, okay. So function spaces they're infinite dimensional spaces. They're kind of weird, and you can certainly construct examples of sets that are closed and bounded but not compact. Here's an example. Yeah. Yes. So G is not in this particular epsilon neighborhood. It might be in a bigger neighborhood. It's not in this one. Okay, excellent question. So let me show you a set that is closed and bounded but not compact. Here's one. Here's a set of functions. Let's take a function that has a spike at, I don't care, how about the point n, and let's call this function fn. And let's say we're going to limit ourselves so that it lies between n plus a half and n minus a half is the only places where it's non-zero. So suppose I look at all such functions. Would you agree they're just a bunch of spikes like this, yes? Etc. Yes? Let's look at this set. Let's call this set A, which is the set of all Fn for n and z. I claim this set is closed. Why? Take a little ribbon around this set, around one of these functions. If you take a ribbon around one of these functions of size, let's say, I don't know, something small, less than a half, would you agree that none of the other functions live inside it, that ribbon, a tiny ribbon? Oh, so this set has no limit points. So it's closed. It's infinite also, yes? Is it bounded? Well, what's the distance between any two functions? At most 1. Oh, so it's bounded, it's closed. In fact, the topology, if I can use that word, induced by this suprema metric on this set looks just like the discrete metric, doesn't it? So if you wanted to cover it with an open cover that has no finite subcover, take little ribbons. That's an open cover of this set with no finite subcover. Okay, good. So hopefully I've convinced you this is not an arbitrary fact, but it is a fact about Rn. All right, let's take a couple-minute break, and after the break, I want to prove a couple more important theorems about compactness.